give you that's basically they'll give you a distance, and they'll maybe give you some attenuation, such as HVLs, TVLs, and maybe a decay calc, which I'll just symbolize with like a half-life or something like that. But in general, what I like to do first is find out the exposure at a particular location, and that's using, or the, they'll give you an activity, obviously. They have to give you an activity. And that's using this formula. Oh shit, I go backwards. Right? Mm-hmm. So this is the formula you guys are, and sometimes they'll throw in a time. Because if this doesn't have the time in the formula, then it just becomes exposure rate, and that's simple. That's shorthand. You put the dot over it, that means rate. So basically, instead of being Rankins, so this formula gives you Rankins, right? If it didn't have the T, it would give you Rankins per hour, right?
Right.
Because you're not multiplying by a time, so you can't. It has to be per hour. It's a rate. So first, what I like to do is, when any problem, they'll give you all this stuff. I like to write out, the exposure, and pick out all of the things that they're talking about in the problem. Right. They're going to give you a number of HVLs and half-lives and stuff like that. Just write it all down so that you have it organized. Then the first thing I like to jump on is say, hey, what is the exposure at a particular location? I like to figure that out first. Once I figure that out, then I try to incorporate all of these attenuations and permissible limits, this is basically going to give you your inverse square that you're going to be using, your distances. And that's what I like to attack or figure out in the second part of the problem. But initially, I need to figure out an exposure. And the reason I like to do that is because, again, that's kind of like our reference of we need a number at a particular location. Once we have that number, that's kind of like that's your reference. From there, you can work it any way you want, and you can figure out what your dose is anywhere else. So let's go to the homework that we talked about. And let's pick out I don't know if do you guys have this, the transmission calculation?
Yes, sir.
All right, let's go to number 3. It starts with 240 milligram radium equivalent.
Uh-huh.
See how we jump right into that?
Right.
Great. So
Three.
Do everyone kind of want to read that out loud or to yourselves, or read it so it makes sense? Don't just read it. Like, read it so you actually are thinking about what numbers are you picking out. Write them down. You may want to get a fresh sheet of paper and not use it exactly on there. So let's write down everything that we have here. So we're given
240 milligram radium equivalent.
Okay, so let's stop right there. So what is that in terms of, what is that value?
That means you have enough iridium seeds to equal radium.
Correct. What quantity does that represent, though?
Your activity.
Exactly.
240
So we have our
milligrams.
activity as 240 milligram radium equivalent.
They are in a teeny tiny box with a radius of 10 centimeters. So I would say my distance is 10 cms. Yeah,
okay.
I mean it's
okay, so you have your distance, 10 cm.
Right. How many 10th value layers of shielding be placed around the source to reduce exposure rate on the surface of the container to less than 2 milliroentgens per hour?
Okay, so they're saying, so what they're looking for is how many TVLs. So I wrote TVL question mark, that's what we're looking for. And we want to reduce the exposure rate to less than 2 milliroentgens per hour. So we want our exposure rate, in this case we put X dot, we want it to be, let's just say 2 milliroentgen an hour. It's really that or less, but let's just say for sake of simplicity, equal to 2 MR an hour. So, let me draw a picture of what's going on here, because that is important in figuring out where to go. You guys have to visualize in your mind what is the setup of this problem. So we have here a source, right?
Right.
It's in a shipping container
Right.
with, that's 10 cm away. And basically we have a certain exposure right here. And what we want to do is we want to create a thickness within this wall such that the exposure rate here is no longer the exposure rate it was without any wall, such that it gets knocked down to 2 MR an hour. So, starting again from the way I like to do it, I say, what is the exposure at a particular location first? That's always where I like to start. Once I figure out what the exposure rate is here, then I know how much do I have to knock it down in order to get it to 2 MR. And that's, so first I'm going to attack is, what is my exposure rate? What is it at this point, which is going to involve some inverse square? Then I'm going to say, okay, how many TVLs is that? The TVL I'll handle in the second part of the question. But that's my thought process. Is everyone following that?
Mm-hmm.
So we're given, so let's solve the first part. How do we get the exposure at that point 10 cm away?
We just take the 240,
Okay, so we take the
Times.
240,
the 8.25.
okay, times the 8.25. Does everyone see how she's doing that?
Right.
Divided by 10 cm squared.
Divided by 10 squared. She's using this formula, right? So this is actually flipped. It should be the 8.25 times the 240 over the 10 squared, right?
Right.
Now keep track of your units here.
Right now everything is milligrams and centimeters, right?
Everything is milligrams, centimeters, yes, and the most important one. What did all this, once you do this, what do you get? You're giving x. What's x going to be in?
Millimeters per hour.
Sorry?
Yeah. I mean, we're trying to get to milliroentgens per. If you have 2 milliroentgens per hour.
We're only in Rankins right now, I think.
We're in Rankins, correct. This is going to be Rankins. Because you can look here, this, remember, what are the units of this right here?
Rankins.
Rankins per hour per milligram at 1 cm, right?
Right.
Squared.
Right.
This one is the milligrams, right? Because it's milligrams Rankin.
Yeah.
So the milligrams are going to cross off. The Rankins, the Rankin's not going to cross off. The CM's going to cross off because this is CM squared.
Mm-hmm.
So we're left with Rankins per hour. Right? So if you work this number out, what do you get? 240 times 8.25 over 10 squared.
19.8.
So 19.8 R per hour.
Mm-hmm.
That's what the exposure is right here. What do we want the exposure to be?
Milliroentgen.
Well,
Less
yeah, less than 2
less than
MR
2.
now.
Yeah,
Right.
Right.
So now does everyone catch the little problem that we have here in units?
Right.
Right.
This is in Rankins per hour, that's in millirankins per hour.
Right.
Mm-hmm.
So we have to convert this to Rankins or this to millirankins. What do you want to do?
Convert the Rankin to milli.
That's easier for me. You could
Because
do it
that's what the
either
answer
way.
is.
For me, it's easier to do that. Convert it to millirankin. So how many millirankin would this be? First, don't say a number, but think about it. Would it be more or less than what it is right now? If this is 19.8 rankins per hour,
Right.
according to millirankins,
Right.
would it be more or less millirankins?
It's going to be more.
More millirankins, because it would be more of these little tiny rankins, right? Exactly. So, how much more?
1980.
1980. Okay, yeah, you're doing these conversions very, 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 very quickly. Good job. No, I think we missed one though. It would be 1,000, right? So wouldn't it be 19800
Okay.
millirankins per hour? I'm gonna write it up here now.
Okay.
I'm going to erase all this. So we have 19,800 millirankins per hour.
Right.
And now we want to get this down to 2 MR an hour. So basically, we want to multiply it by a certain.
1/10.
I was gonna say point one.
Okay, 1/10. So we want to multiply by a certain number of 10th value layers,
Right.
right? So 10th value layer is very similar to a half value layer. Half value layer is the thickness of material that knocks down the intensity from its original to 1/2. 10th value layer will knock down it's the thickness of material required to knock it down to a 10, right? So we can say how many 10th value layers would get us to 2. If we take 1 10th value layer, let's just do this let's just do it the long way first. Ignore this. Or this is Andrea likes to do it this way a lot. And if I do it by 1/10th value layer,
Then I get what?
what do you
Right.
get?
Everyone.
Everyone-
1980.
My calendar.
Right.
My calendar. 1980.
Okay, so you get 1980. And then if I do by another 10th value layer,
198.
when
Uh-huh.
Lynn's just doing it quickly by knocking
Right.
off zeros. She's just moving
Right,
the
right,
decimal. So if I did another 10th value layer, it would be
19.8.
19.8. If I did another 10th value layer, it would be
1.98.
1.98. Now it's less than 2, right? So this would
Five.
be 4
4.
4 TVLs,
Mm-hmm.
right? This is the kind of conceptual way to do it. The mathematical way to do it is saying 1/10 to how
It makes more sense to me to see it. To how many I don't do.
the number of TVLs. So that's kind of the way that I think about it. It's basically you're saying how 1/10 raised to some power. I called it number of TVLs, or we can call it, let's call it
What the hell is that?
My chair.
let's just call it T, right?
Right.
So now we're saying 1/10 to some power equals 2. How can we solve this? This is going to take some mathematics, some special math
Yeah,
that we
takes-
talked about.
Like special math.
All right.
like the special math.
So this is going to involve not natural logs, but logs. Natural logs is when we have, remember when we're solving for, when we have, and basically this is an
Yes.
equation with an unknown in the exponent.
Okay.
Typically we have our unknowns in the exponent with e to the minus, mu x or something like that equals I over IO, right? And if we're looking for a thickness or something, we have e to that power. So in this case, we take the natural log of both sides, right? Remember this little math trick?
Yeah.
In this case, our base is not e, so we don't have to use natural logs. In this case, our base is a number, so we're going to use
Log.
logs. So,
Would you divide the 18
My
or the
way.
19800 by 2 before you do anything else?
I would actually divide the 2 by 19800. Because what I want to do is I want to
You wanna get
separate
that on the
this
other side.
on the other side. So I would say 1/10 t equals 2 over 19800, right?
Okay.
Now, this equals what? Some number?
0.0001.
Okay, let's just leave it then. Let's just leave it as it is. I'm going to rewrite it because I need to squeeze something in here. 19800. But now, for me to, actually I can write down here. If I take the log of both sides, this becomes t log of 1/10 equals log 2 over 19800. This is the same thing as the e. When you take the e of a certain number, the exponent comes down and it becomes natural log, becomes a log of e. Remember the natural, sorry, the natural log of e is always equal to 1. So in this case, we don't write it. We just write whatever was in the exponent because we brought it down. Remember that little trick?
Mm-hmm.
And you guys eventually probably forgot about that. This is what you were doing. And you would just take the exponent.
Right.
But really, you're taking the exponent down and you're taking the log of that number. In this case, it's the log because it's an actual number. It's not e. That's why it's not natural log. Anyway, you take the log of both sides. So now this becomes a number and this becomes a number, right? Alternatively, you can rewrite this. You can bring this thing down here, and you can say the log of 2 over 19800 over the log of 1/10 is going to equal your t, and that will give you your number of 10th value layers. That if you do this, I want everyone to actually plug this into your calculator
Okay.
and see what you get.
I got like negative 3.9.
Negative 3.9. It should be positive 3.9. Somehow there's a.
Oh, sorry. Yeah, 3.9. Positive 3.9.
3.9.
Yes.
So what it's saying is, did everyone get that? Oh wait. Is everyone following this math? I know this is a hard way to do this problem, but that's because I gave you simple numbers. If I didn't give you easy numbers, if I were to say how many 10th value layers will give me, and it,
1.6.
1.6,
Yeah.
yeah. Anything else, then this would be 1.6 now. You can't just figure out by
Well,
doing it the other way.
I mean, I guess it depends on how close the answers are. 'Cause
Well,
you
yeah.
reverse